topic we'll be talking about in this lecture will be bond, polarity, and the formal charge. Okay? Now the first question states, which of the following bonds are polar? So we're going to figure out which one of these four bonds is going to be polar, and then which is the more electronegative atom in the bond. All right. So remember, in order for a bond to be polar, there has to be a difference in electronegativity between the two atoms which are constituting the bond. So for part A, we have boron and fluoride. For part B, we have chlorine and chlorine. For part C, we have selenium and oxygen. And for part D, we have hydrogen and iodide. So we're going to start working through A. We'll determine we'll go through and determine which ones are polar, and then what is the more electronegative atom in them. So if we have boron and fluoride, there's going to be a difference in electronegativity, and so this is going to be a polar bond. Now, which one is going to be more electronegative? Well, the answer to this is very easy, is fluoride, because fluoride is the most electronegative species in the periodic table. And so boron fluoride is going to form a polar bond. For part B, we have chlorine and chlorine. Well, since that's homonuclear, there is no difference in electronegativity between the two of them. This is going to be a non-polar bond. And since it's homonuclear, they're equal polarity, or they're equal in negativity. In part C, we have selenium and oxygen. Now, selenium is going to be below oxygen, and so oxygen is going to be more polar, making this a polar bond, and the oxygen is going to be the more electronegative species. We have hydrogen and iodide. Iodide is going to be fairly far down the periodic table, but because it's a halogen, it's going to be more electronegative than hydrogen is. And so iodine is going to be the more electronegative species, thus resulting in this bond being polar. Okay? The next problem we're going to do will be dealing with formal charge. How do you calculate the formal charge? For this problem, what we want to do is we want to calculate the formal charge for the indicated atom. Now, the indicated atom I have actually underlined in each of the following molecules or ions. So the first one we're dealing with is we're going to be dealing with phosphorus hexafluoride. Phosphorus hexafluoride. The first thing I do when I'm trying to determine the formal charge, I'm going to count the number of valence electrons. And we know that phosphorus is going to have 5. We have 6 fluorines. Each fluorine is going to have 7. Now here's going to be an additional electron, so we add 1 to that. Therefore, the total number of electrons here is going to be 48 electrons. And the next thing I'm going to do is I'm going to draw the Lewis dot structure for this molecule. And so I'm going to have the phosphorus being in the center because it's more metallic. If you ever have a problem determining what is going to be the central atom is going to be the one that is most metallic. So remember, that's going to be to the left on the periodic table and lower on the periodic table. So here we put our fluorines, fluorines. Now we're going to put the valence electrons around the fluorines. Okay? Now each one of these bonds is going to have 8 electrons. So there's 8, 8, 8, 8, 8, and 8. And 6 times 8 is going to be 48, so there's our 48 valence electrons. And now what we want to do is we want to come up with the formal charge for the phosphorus. For the formal charge, that's going to be the number of valence electrons. So for the formal charge, this is going to be equal to, I'll write down here for more space, the number of valence electrons that phosphorus has is 5, minus the number of lone pairs, where there are 0. The phosphorus does not have any lone pairs, minus 1/2 the number of bonding electrons. Another way you can say that is the number of bonds to it. So let me repeat that. It's either 1/2 the number of bonding electrons or the number of bonds to it. So here we have 2, 4, 6, 8, 10, 12, or 6 bonds. That's 5 minus 6, and this gives us a formal charge of the phosphorus of -1, which happens to be the charge of the entire polyatomic anion. Let's now work with nitrogen dioxide. Once again, I'm going to do the exact same thing I've done before, and I'm going to count the number of valence electrons. Nitrogen has 5. Each oxygen is going to have 6. And since I have 2 oxygens, that gives us 12. And so the total number is 17 electrons that we have to take into account. Since nitrogen is further to the left than oxygen, nitrogen is going to be our central atom. It's going to form a double bond with the oxygen. With one of the oxygens, and with the other oxygen, it's only going to form a single bond. Now, if we start counting up our electrons, we have 2, 4, 6, 8, 10, 12, 14, 16. And so there's a lone electron, which is called a free radical. An unpaired electron is called a free radical on the nitrogen. Now, the reason nitrogen doesn't have an octet is because there just aren't enough electrons. You say, but wait a minute, why can't it take an electron from oxygen? The reason it will not take an electron from oxygen is that oxygen is more electronegative. If nitrogen tries to take that electron from oxygen, it won't do it because of the strong electronegativity of the oxygen atom. Therefore, nitrogen is going to be the one that's sort of left out. Now we want to come up with the formal charge of nitrogen. Once again, the formal charge is equal to 5. In this case, nitrogen has 5 valence electrons. It's right above phosphorus. Minus the number of lone electrons. In this case, it's going to be 1. Minus half the number of bonding pairs, or the number of bonds. So this becomes 3. Has 3 bonds, 1, 2, 3. Or you can think of 2, 4, 6. Half of 6 is 3. And this is going to give us a formal charge of +1. 5 minus 1 minus 3 is going to give us a charge of 1. So the formal charge of nitrogen in this case is going to be +1. We have a couple examples here. We're going to be looking at the formal charge of iodine in iodine trichloride, as well as the chloride's formal charge in perchloric acid. So let's get started. First thing we want to do, once again, is we're going to calculate the number of valence electrons. So iodine has 7. Each chloride has 7. So 4 times 7 is going to be 28 valence electrons. Now iodine is going to be the central atom because it is more metallic than chloride. It's going to be a couple elements below. So we put the iodine in the center, and then we bond the chlorides around, and then we're going to fill the valence electrons around each chloride. We have 8, 8, and 8. 3 times 8 is going to be 24. So we're missing 4 electrons, and we're going to place them around the iodine. The reason we're going to place them around the iodine is because it's the central atom. It also is going to have a principal quantum number greater than 2. And because of that, it can put electrons into its D shell. It even can potentially put electrons into its D shell. So in this case, iodine can have an expanded octet in which it can entertain more electrons in its valence shell than its standard 8. Now we want to come up with the formal charge of iodine. So formal charge for iodine. Iodine is going to have 7 valence electrons minus the lone electrons, which is going to be 4, minus 1/2 the bonding pair, or minus the number of bonds. In this case, that happens to be 3. And the formal charge for iodine is going to be 0. Now we can go down here to the perchloric acid, and if we're going to count the number of valence electrons, hydrogen has 1, the chloride is going to have 7, and each oxygen is going to have 6. And this gives us 32 electrons. 32 valence electrons we have to account for. Now, the way the formula was written here, we know that the chloride is going to be the central atom. And in the instructions, it says that the hydrogen is going to be bonded to one of the oxygens. So we can just do that right there. Now, we have to account for the oxygens. All right. Now it's where the formal charge becomes sort of nice. In lieu of time, I know that each one of these is going to have a double bond, and we'll see if I'm actually right. If I'm not right, then the charge on the chlorine will be something other than 0. Because this is a neutral molecule. Now, if you do the formal charge of each one of these oxygens, doing the exact same way, do the formal charge of each one of these oxygens, this oxygen will have a formal charge of 0, this oxygen will have a formal charge of 0, this oxygen will have a formal charge of 0, that oxygen will have a formal charge of 0. Now remember, there's a bond between here, so if we start counting the electrons, we're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we now have 32 valence electrons, which is what we predicted. Now let's determine the formal charge of the chlorine atom. So the formal charge of the chlorine atom is going to be equal to the chloride is going to have 7 valence electrons. It doesn't have any lone electrons around it, so that's going to be minus 0, minus 1/2 the bonding pair, or bonding electrons, or the number of bonds. So this is 2, 4, 6, 7, minus 7, and therefore the formal charge of the chlorine is going to be 0. Now, you may say, wait a minute, the chlorine has 14 electrons around it. 2, 4, 6, 8, 10, 12, 14. You're exactly right. But it has a principal quantum number greater than 2. Because it has a principal quantum number greater than 2, it can entertain and hold in more than 8 electrons into its octet, or into its valence shell. So it can have what's called an expanded octet. All right?